Hi everyone, I'm going to demonstrate how to use the CG50 to plot this data and to straighten the data. So the situation is we have this is Galileo's famous experiment where he watched the chandelier swinging in the cathedral. So it's basically a pendulum with different length and a different time period to swing back and forth. We need to go into stats mode and then enter the raw data in the lists. So the first list I'm going to use as length, and I'll just put the letter L at the top there. Doesn't make any difference whatsoever to the calculator, it helps me remember what's going on. So the length data in list number 1. In list number 2, once again, I'll put a label here so I don't mix things up down the track. And what have we got? 1.1. There we go. Now, at a first guess, I might try plotting the period. Just do a little sketch here. What if I plot the period versus the length of the pendulum? And see what we get. Now, whenever you plot, remember to check the settings first. So I've got 3 different graphs I can use. This is the stat number 1. It's a scatter graph using list 1 for X and list 2 for Y. Frequency of 1 is good. It means that every data point appears once. So I can, now that I've checked that, I can just select graph 1. There it is. Now that looks a little curved to me, slightly curved. I could do a calculation and then I go into X and I do a regression line, a linear line. Look, 0.99 is pretty good by anybody's standards for a correlation coefficient, but when I draw that line, notice that the data point at the beginning is below, the 2 in the middle are above, and the one at the end is below. That is pretty characteristic of the fact that we have a curved set of data going on here. If this really was linear, you'd expect these data points to be randomly above or below the line of best fit. So my graph of P versus L, I think, is... where did my pen go? I think my graph of P versus L is a curve that looks like this. How will I straighten the data? Go back to here. Now in list number 3, I will ask it, so I've got to go up to the heading. I'm going to ask it to calculate the logarithm, and I go, oops, I didn't mean press trace, so I'm going to shift 1 for the word list and then 1. I'm going to ask this to calculate the natural log of all of those values. There they are. For list number 4, up to the very top, I want the natural logarithm of the numbers stored in list 2. There they are. I'll check the settings for stat graph number 2. It's a scatter graph using list 3 and list 4. That's what I need. Exit from there. Graph number 2. There's my line graph now. And my line graph this time, if I just go back here, I'll get rid of that. My line graph now is the natural logarithm of the length versus the natural logarithm of the period. And it does seem to be pretty much a straight line graph with my data points, some negative, some positive. Let's do the calculation and we'll put a straight line fit. The correlation coefficient this time is 0.999. It's a better fit. And importantly, I want to know the value of A and the value of B. So I'll draw that one in. It does look like there's no obvious curvature going on. And so I'll pop back to here so we can see these numbers. Now, what do we do with these numbers? Well, our equation is the form y equals A plus B times X. That's nice. Oh, why did it do that? It's crazy. What was the y variable? Well, the y variable was actually the natural logarithm of p. A is the number 0. Well, I'm going to call that 0.694, plus b is the number 0.502, and that was multiplied by the natural logarithm of L, because we had lnp for the y-axis and ln of length for the x-axis. Now we better try and neaten this up somehow. So I'll write this as ln of p equals. Now how can I make the number 0.694 look like a logarithm? Well, I would have to write ln of e to the power 0.694 and that 0.502 would be best off if I write this as ln of L to the power 0.502. So ln of p, now I could write the right hand side as a single logarithm, e to the power of 0.694 times L to the power of 0.502. Now the fact that we've got natural logarithm of p equals the natural logarithm of all these things, it should be very obvious then, I hope, that p equals e to the power of 0.694 times L to the power of 0.502. Now don't forget that e is a number. So if I just pop back to my main screen for a minute, well, that's something that I did before, don't worry about that. Yes, I want to get rid of everything there. Right. So if I go e to the power, where are you? There you are, of 0.694, I see that this coefficient here is really 2.00. So it's much neater to write this as 2 times L to the power of, now I must admit the 0.502, there's probably a little bit of measurement uncertainty in these. How many significant figures do we have in each of these? Well, 2 in most of them, only 1 here and 1 here. So I'm probably pushing the luck here to write 3 figures of accuracy. If I were to round that to 2 figures, it's 0.5, and so I think we'd be quite justified in claiming that this is the square root of L. There's my formula. The period of the pendulum equals 2 times the square root of L. And that's how you straighten the data, by plotting a log graph of the 2 variables. And then remember, we were in the stats app. We entered our raw data in the lists. We took the natural logarithm of both. When I did the graph, I made sure to have the settings of the second graph to use the third and the fourth list. So then when I select the second graph, I get this. I can do a linear regression line. There's the value of A, there's the value of B. The correlation coefficient is very good, better than when I just fit the raw data. And particularly important, I don't see any fixed pattern with the residuals here, which makes me confident that this is a good model. That's all.